So what I have right here on my desk is a Power Designs Model 4010 power supply. And in this video, I'm going to kind of try to diagnose and repair this power supply. I bought this at an estate sale for $27 for basically nothing. I was actually intending to buy some other things at the estate sale, and I stumbled across this when I was scrolling through, and I thought it's a really cool looking unit with this combination voltmeter and ammeter over here, and these dials to set the voltage and whatever. It has a very nice industrial kind of look to it. All metal, brushed metal faceplate, very, very high quality. It looks like a real piece of nice laboratory equipment. So I decided to pick it up. The more research I did into this thing, there's actually a thread on EEV blog where someone's referring to a book, and in the book they tested a bunch of different power supplies to figure out which one had the lowest noise. And that included, modern power supplies from Agilent, old HP stuff, and whatnot. And of the units they tested, this had the lowest noise at something like 1.5 microvolts, I think it was. The lowest except for a lead acid battery. So this is a very, very low noise power supply. It doesn't do a lot of current, and it doesn't do a lot of voltage. As you'll see here, it's 40 volts DC at 1 amp maximum. And Power Designs made a lot of these, low current, low voltage, high precision power supplies. There's 20 volt, 500 milliamp ones, and a bunch of others on the internet. The 4010 is actually a really rare model. If you search Power Designs 4010, one of the things on the first page of the Google results is the auction listing for the unit that I bought. So there's really not much out there on these at all, and they don't seem to crop up very often. Some of the other Power Designs models are far more common than this one, but there's not a lot of documentation or anything on this power supply. In fact, I can't even find a full schematic for this, unfortunately. So I think what we're going to do, well, first I'm going to show you what's wrong with it. And I have a suspicion that I might know what's causing this problem, but we'll see. And then I'll show you what the inside of the unit looks like, and we'll see if we can repair it. So yeah, so the first thing I want to do is just turn this on and show you what's the issue. Now, you'll note that the oven light is going on and off. This power supply actually has a heated oven that is used to, temperature stabilize the voltage references and some of the other components in here. This thing is very stable as well as being very low noise. So it actually has an oven inside, and there's a kind of a voltage reference amplifier inside the oven that helps set the voltage. So this thing has very low voltage drift over time. So that's one of its characteristics. But so anyways, you'll see this oven light going on and off. Obviously, one of the minor things I have to do is replace this oven bulb because it's going out. And the oven goes on when the unit is plugged in. It doesn't respond to the switch, so whenever the unit is plugged in, you've got the current going into that oven. But if I turn this on, so you can see I have my multimeter set up over here. Right now it's reading 0.3 volts. I actually had this on earlier, and it has a big cap across the output, so it actually stores voltage for quite a while. But yeah, so you can see it's reading 0.3 volts, but we do have the actual output of this set to off right now. So let me just turn it on, and you'll see what our issue is immediately. So this is set to 20 volts, as you can see here. We've got 2 on this dial, 0 on this one, 0, 0. So we should have 20 volts DC here. However, when I turn this on, you'll see we have 44 volts. Not good. And if I lower this, you'll see it goes down, but not far enough. It goes down to 22 volts. And another thing you'll notice is that the voltage incrementation, it's not like there's an offset that's incorrect. It's not like the voltage output is a set amount higher than it should be. It actually increases disproportionately. So if we increase the reading on this dial here from 10 to 11, let's see what we get. We have 25 volts now. If we increase this from 10 to 11, we had 22.5 before, sorry, and now we have 25. Let's try increasing this again. Now we have 27.3. So you can see that in addition to the voltage being off and being too high, it actually also increases at a disproportionate rate. So there's some sort of an issue here with the voltage setting circuitry clearly. And I will be able to use the fact that the voltage isn't increasing and decreasing by the correct amount, I think, to rule out a certain kind of fault that might have been the culprit with this power supply. Before we move on to looking inside the unit, I forgot to show one other thing that I should show, which is that we don't have a ton of ripple on the output of this power supply. So I've got it on again, and I've got it set to 10 volts, as you can see. And I've got the multimeter at the right set to display AC voltage. And you can see we have about 30 millivolts of AC. Certainly not as low as it probably should be, perhaps, but also this isn't really a proper measurement setup. You know, I've got my test leads very long all over the bench here, not really conducive to low noise measurements. It's also not loaded down very much, it's just loaded by the multimeter. So, you know, we could take a proper noise measurement later, perhaps, but suffice to say, it's not like we have a volt or 2 volts of ripple. We don't have any symptoms of a massive capacitor failure or anything. All right, so before we get into attempting some diagnostics, I do want to just kind of do a quick tour of the unit and how it's constructed and how it works, because it's a pretty cool little power supply. And so yeah, so of course here we have our combination voltmeter and ammeter. This little switch controls whether you're displaying volts or amps. Then here we have a potentiometer that sets the current limit. Pretty simple. It feels to me like a wire-wound potentiometer based on you can kind of feel the wiper going over the wires inside of there. Here we have our light, which I assume goes on when the current limit is reached. We have our oven light, which goes on whenever the unit is plugged in, and then we have our voltage setting switches right here. So yeah, so they have an inner dial kind of switch here that you set as such. And then they have an outer one, which you set by gripping the outer ring and moving it like this. And I'll show you, of course, what they look like on the inside of the unit in a second. And you have a little window, of course, which displays whatever setting you're on. So yep, so those are used to set the voltage. And then here for the 0 to 10 millivolts adjust range, you have this really cool little potentiometer down here, which I think is kind of a multi-turn unit. And what you'll see is that it has this outer ring that shows the millivolts, and then an inner ring that shows the fractions of a millivolt. So right here you can see we're on, so if I turn it to, this is 0.0 millivolts. Let me just zoom in there so you can see, because it is pretty cool. So right now you can see something's wrong with the mechanism, so it's not totally centered, but the outer ring is not totally centered, but you can see here this is 0.0 millivolts. Now when I turn this such that it reaches 0.9 millivolts right here, and then I turn it a little more, you can see it adjusts the outer ring to 1 millivolt. So yeah, that's a really cool little mechanism right there that gives you kind of a graphical representation of your adjustments. And of course, this is a very fine adjustment. This is some sort of a multi-turn potentiometer. On the inside, you can see it's a really big looking potentiometer. And I don't know what the mechanism looks like inside of here, but it does the same thing as you increment downwards. I hope there's a way that I can adjust some of these mechanisms such that the numbers align better, with this little marker and whatever, because some of them have become a little bit out of alignment. Although this looks pretty good right now, actually, when I'm doing it now. But yeah, cool little mechanism there. And then, of course, over here we just have our switch that's labeled AC on, although it's actually kind of funny because the AC supply to this is on whenever you turn it in and the oven goes on. It would make sense to me to call this DC on, because what this really toggles is the output, whether or not the output of the supply is on. But in any case, it is called AC on. I'm sure it is an AC switch that, actually I'm not sure it's an AC switch. I'm assuming it does switch the AC, and the transformer that supplies, or whatever power supply supplies the oven, is just before this switch, but I'm actually not certain about that. And then here we have our output binding posts, and since this unit does have a floating output, in addition to DC plus and minus, we have a ground post at the bottom right here, which of course I'm not currently using, but that is something that is available for use. So yeah, pretty simple front panel, really just has everything you need and nothing you don't need. All right, so now let's take a look at the inside of the Power Designs 4010 from the top. So what we have right here, this might look like an electrolytic capacitor, but this is actually the oven, the so-called reference amplifier oven that contains the voltage setting circuitry and the voltage references, and keeps them at a stable temperature to minimize temperature-related drift. Right here we have the electrolytic filter cap, and this is an electrolytic cap that goes across the output of the unit. And then in here we have another electrolytic capacitor. I'm not actually entirely sure what this one does. Of course, it's a linear power supply, so we have our power transformer right here. And then we have, of course, this is our main board that handles all our circuitry, that holds all our circuitry, and that is not a PCB. As you can see, there's actually wires going all across this board, so there are no traces, there are no copper traces on this board. This is point-to-point kind of wiring using eyelets, and obviously a very old, labor-intensive style of wiring, but the PCBs of this era, and there were PCBs made at this time, but they just weren't that great in quality in many cases, and so I think this was a high quality method of wiring that was suitable for kind of low production volumes. Also, you can see all our wiring is in these really nice, pretty wiring looms right here. This is like what you would see in old, lots of old tube gear that has point-to-point wiring. In high quality stuff like, Western Electric, that type of thing, you get these really nice wiring looms. Well, you have one of those here too. And yep, we have a few big wire wound resistors on here, and we have, I think this is a film capacitor, if I remember correctly. Yeah, so that's kind of some of the basic components in this thing. All right, I've zoomed in a little bit on the front side of the unit here that's on the back of the front panel. Just to take a closer look at a few things. So this right here is the combined voltmeter and ammeter that we saw on the front. It is a General Electric manufactured meter, and I really like how it looks, and it still works well, which is kind of rare for analog meters, so that's nice. These right here are rotary switches that are used to set the output voltage of the power supply. And I'm going to talk about this a little bit more when we go to the schematic and when we take a closer look at how this thing works. But yeah, so when you adjust the rotary switches on the front, to set the output voltage, basically all you're doing is switching resistors in and out of a circuit. And there's a voltage control circuit, and there's a resistance that goes between both the outputs of the power supply. And based on the resistance between those outputs, your output voltage gets set. So the programming resistance is actually 1,000 ohms per volt. And we'll see this in a second when we look at the back, because you can actually program this thing externally using your own resistors in addition to these ones here. But anyways, the resistance is 1,000 ohms per volt. So if you have 10,000 ohms through these switches, you will have 10 volts on the output. If you have 15,000 ohms, you'll have 15 volts, and so on. And so what these switches are really doing is just, taking resistors in and out of the circuit, and doing that gives you your output voltages. It's a very simple system, very simple way to set the output voltage, and it is quite expensive to manufacture as well, because you will note that these are precision resistors. If I can zoom in on this here, you can see 0.01% spec on these resistors, and look how many of them there are. There are really quite a lot of them. So this is a very, very kind of expensive way with these big rotary switches and all these precision resistors to set the output voltage of the power supply. But of course, this is kind of a, really high-end piece of test gear for its time, so they're probably not too concerned about that. But yeah, and then there is the potentiometer down here. You can't really see it. I think we'll get a better look at it later, but that's the one that sets the millivolt range. And yeah, it's just a really big, some sort of a multi-turn potentiometer in there. Actually, before we flip this over and go to the bottom, I just want to show you what the side looks like. Not much to see here, except we have our TO3 pass transistors mounted in this little cool little indentation here, and with a kind of circular, I think, mica washer, which I haven't really seen before. You can kind of see it there. It's like shiny. But anyways, yep. MS1700 Motorola transistor mounted in that little indentation here that prevents the case from interfering with the transistor. Kind of cool. Here on the back panel, there's not too much to see. We've got a fuse, we've got a bunch of instructions. There are sense terminals if you want to use like remote voltage sensing. So we have sense terminals and jumpers that you can use to connect or disconnect. The sense terminals, I just have them jumped right now, so the sense is just being done internally. And then, of course, at the bottom left here, what I wanted to show is that we have our programming resistance right here. So if you remove this jumper, then you can add additional resistance into here that goes in series with whatever resistance you're setting using the switches to set your voltage using some external resistor if you had a reason to do that. I can imagine in some sort of a production environment or whatever, if you want to design a better switch that just has exactly the voltage you need, you could do that. And of course, you can see right here, external resistance, 1000 ohms per volt. So yep, that's all I really wanted to show on the back panel here. All right, so before we take a look underneath the Power Designs 4010, I want to form a hypothesis about what's wrong with the unit. And to do that, I want to take a look at the schematic. This is the schematic for a Power Designs 2005A, not the 4010. I cannot find a 4010 schematic on the internet. I think it's a pretty rare model, and there isn't a schematic available online, but I did find this 2005A schematic. And the 2005A looks very similar from the front. It has the exact same type of rotary switches to set the voltage. It's overall looks extremely similar, but it just does 20 volts instead of 40 volts and 500 milliamps instead of 1 amp. So half the voltage and half the current. So it's just kind of, I think it's just a lower end, lower spec model with less voltage and current capability, but overall very similar in design. And there's some common components here and layout things that I see also in my 4010 that make me think that. For example, our series regulator transistor right here, the power transistor, the TO3 transistor, is the MS1700, as you can see. And that is the same type of transistor that we have in the 4010, except there's 2 of them instead of 1, so double the current, double the transistors. Kind of makes sense. I think they're very similar designs, just with changes made to accommodate the extra voltage and current. So I think we can look at the principles of this 2005A, and they will be valid for the 4010. Of course, no need to reinvent the wheel. I think Power Designs was just kind of making the same sort of design, just with different voltage and current capabilities, which makes sense. So this is all the driver circuitry and all the amplifier circuitry for the regulation. And I think that it's safe to say, based on the results we observed during our test, we have very low ripple. And I don't see any indication that the regulation itself is broken. So I don't think our issue is in any of this circuitry, although it could be. What I suspect, and this right here is the current limiting circuitry. We didn't test that. That could be broken, but that's not the primary issue we're investigating right now. So I think we're going to ignore this too. So all this stuff I don't think matters too much. What we want to take a look at is the voltage reference and control circuitry, which is all up here. And you can see this dotted line represents everything that is inside of our temperature controlled oven. And then right here we have our oven driver circuitry, which also could be broken, but the oven does get warm, and I'm not super concerned about, the voltage stability being exactly up to the, the spec and whatnot. If there is an issue with that, I could take a look at it in a future video, but right now I just want to get this thing working and having the voltage set correctly. So we're going to focus in on all the stuff that's inside the oven, which logically is all of the stuff that sets the voltage and contains the voltage reference for the unit. And then just over here, I want to point out right here, we have our rotary switches that are used to set the output voltage of the power supply. And you can see we have all these precision resistors. They're spec'd here as 0.1%. Actually, we saw one in there, 0.1%. We saw one in there that was 0.01%. So I'm not sure if that was just maybe they had higher spec resistors on hand, or I'm not sure what the deal was there, because I don't see any 0.01s on anywhere on the schematic, but we do have one in the unit that I have, which is interesting. Oh, there is a point, but this is the wrong resistor. This is a actually, this is a resistor that's used to set the voltage range here. So that could actually be a similar thing. Maybe only the high value resistors get this 0.01% spec, which would make sense. Of course, this being the 20 volt, this being the 20 volt model, there's only one resistor that selects between 10 to 20 volts, as opposed to, or rather, but this resistor sets a 10 volt increase, being a 10K resistor that's analogous to the 0.01% resistor we saw in the 4010. So that's probably why this is 0.01%, and I'm guessing only the 10K and 20K resistors are 0.01%, and then the other ones are probably whatever these percentages are up here. But anyways, so this resistor kind of network here is what's used to set the resistance that determines the output voltage. So we see a similar sort of thing here. And this method of setting the output voltage should offer us a clue as to what our failure mode could be. Because if you think about it, what would, if any one of these resistors changed in value, like let's say our 10K resistor went to 15K, what would you expect? Well, you'd expect that whenever this resistor is in the circuit, you'll have a 5 volt error corresponding to the 5K ohm error. That would be a fixed error though. If you switched a 1K resistor in, then you would have 16 volts instead of 11 volts, but it would be the same 5 volt offset. You would always have that same type of error because there's no multiplication, there's no non-linearities here. It's just the resistance that you have is the resistance that sets the voltage. So if a resistor goes up or down, you'll have a fixed offset voltage from the correct voltage, but you won't have, a cascading error that causes the other resistors to switch the voltage by an unanticipated amount. Remember, that's what we're seeing. Every time we switch in any of these resistors, the voltage is not only incorrect, but also changes by an incorrect amount. And the only way that would happen is if every single one of these resistors had gone out of spec, which just doesn't make any sense. And also keep in mind that the voltage error we're observing, I think, if I recall, is about 2.5 times too high or something like that. So all the resistors would have to drift high by the same amount. That just doesn't seem very likely. It doesn't really make any sense that would happen. So I think we can rule out an issue with our actual resistors or our switches here by virtue of the way that this failure mode would actually manifest versus what we're observing. And that'll save us from having to, test all these resistors and go through and do any of that. I think we can rule that out. And so what we really want to look at is this portion up here that senses the voltage and also, and handles the setting of the voltage. And we're going to consult the manual because the manual is actually really nice and has sort of a, nice description of how the circuitry works. All right, so now I've zoomed in on the portion of the schematic that shows the differential amplifier and the voltage setting circuitry inside the oven where I think the problem is. So first thing I'm going to do, since I zoomed in, we lost a little bit of context, is I'm going to label a few things. So one relevant thing is this right here, this connection that comes into pin 7. These are the oven pins, these pins right here. This is the DC negative output of our power supply. So this is the negative rail of our power supply output right here, DC minus. Okay, and the other one is this right here, this is our voltage setting resistance. So the voltage setting resistors I'm going to represent right here. They connect to the DC positive supply, and you change this resistance. You change this resistance to change the output voltage. All right, so now that we've got that drawn, let's read a little bit of the manual, the manual's explanation of the principles of operation of this circuit. So the series regulator circuit contains the differential amplifier Q3. Okay, that's this differential amplifier right here. We can tell it's a differential amplifier, of course, because we have the emitters tied together. We have this emitter resistor, tail resistor right here. We have our two base inputs, and we have our collector load resistors right here that are identical. So this is a classic differential amplifier right here. We don't really care about the drivers or any of the other circuitry, since I think that's all fine. A constant current is maintained. Oh, sorry, I missed. The voltage reference for this differential amplifier is Zener diode CR9. Okay, that's going to be this Zener diode right here, CR9. All right. Constant current is maintained through CR9 by these transistors. Not super important, but of course, the Zener diode does need a constant current through it to operate correctly, so we have that. From the divide string of R42 through R73 and R41 and R40, which connect to DC positive, a 1 milliampere current flows to the oven terminal pin 3. Okay, so basically what that's telling us is that, so these are the resistors they're referring to, R42 through R73 and R41 and R40. I've represented them all right here, as I showed earlier right here. That's these resistors right here, and what that's telling us is that this is a 1 milliampere current through here. And it says that's always 1 milliampere, and this offers a clue as to how this circuitry works. Basically what we're doing is this voltage, the voltage that is present at this point right here must be such that 1 milliampere is flowing through this resistance. So for instance, if we have 10k ohms here, this must be 10 volts to flow 1 milliampere. If we have, 20k ohms here, this must be 20 volts to flow that 1 milliampere. So that's how this is supposed to operate. The voltage here is such that you get the correct amount of current flowing through here. All right, let's continue. This current flows through R14 in parallel with R16 and R17 and establishes a voltage at one base of Q3. Okay, so R14, R16, and R17 are right here. So we have those resistors, and we can see, of course, that the current that flows through here, it must pass through these three resistors. So we can see that, and that would set whatever this voltage is. The voltage drop across here would also, set this. All right, let's keep going. The common emitter resistor R13 of Q3 returns to the potential of Zener diode CR9. All right, so the resistor right here returns to CR9, and we can see that if we trace this out right here, it does in fact return to CR9, and also it connects to here, and it connects over to here. So the current that's flowing through here is coming from here as well. All right, so I think at this point it might be useful to draw some voltages. Let's say that our DC output is negative 10 volts. We can see this would be, I'm going to get rid of the decimals, about negative 16. And we also have it here, negative 16. All right, let's keep going. The DC minus connects to the opposite end of CR9. All right, we've got that here. Therefore, the voltage from the first base of Q3 to DC minus is 0. Now, that's not really intuitive necessarily. What they're saying is that this voltage relative to DC minus is 0. However, we'll see in a second why that does have to be the case, and and we'll see that in a sec. We'll all demonstrate why that must be in a second. And that voltage, of course, is getting dropped by these, and that's why this has to be the same, but let's just continue for 1 second. The second base of Q3 is also at 0 volts relative to DC minus by virtue of R15. So we can see R15 here, it's only 100 ohms. So yep, there's very little current flowing here, so with only 100 ohms, this would also be at negative 10 volts. All right, now what I want to do, so we were told that this is at negative 10 volts. The manual says that, and let's explore why that would have to be. Why does this have to be negative 10 volts? Well, if we look at the circuitry here, this voltage difference between this point and this point, this has to be negative 6 because this voltage difference is set by the Zener diode. That's a characteristic of the Zener diode that's like immutable. If the circuit is working correctly, this has to be a negative 6 volt difference. And in order for the supply to be outputting a DC voltage and be in equilibrium and functioning properly, the differential amplifier needs to have equal inputs on both sides. So this difference also has to be negative 6 volts. It's set at negative 6 volts. So what produces the correct programming voltage here is the relationship between these resistances. It's the relationship between these two. Because if these resistors are set up correctly and this is set up correctly, you will see when you do the math, this resistance combines to about 6.3 k ohms. So when 1 milliamp flows through here, it drops 6 volts here. Okay, perfect. That brings us down to negative 10. And then the 1 milliamp continues to whatever the correct programming resistance is here that produces 1 milliamp and gives us our correct voltage here. But let's think, what would happen if these resistors, if R14 and R16 and R17, what would happen if these resistors drifted and they were no longer the correct value? Well, this still has to be a 6 volt difference, as we saw. This is set by the Zener. This has to be a 6 volt difference between the base here and between this negative 16 here. But if these resistances changed, then the current would also change. Let's say these went high. Well, the current necessary to produce this 6 volts would decrease. But what that means is that the current flowing through here would also have to decrease. So the correct relationship between this current and these resistors is dependent on these resistors right here being correct. So my hypothesis for what has happened is that these resistors have drifted in value. And because these resistors have drifted, the amount of current necessary to produce this 6 volt differential right here has changed. And what that does is means that the amount of voltage necessary to produce the right current through this has also changed, and that messes up the whole relationship. And what that will do is now, rather than programming this resistance for 1 milliamp, this resistance is programming for whatever the new current flow is. And if I remember correctly, based on, kind of thinking this through earlier, if these resistors go low in value, this current increases. And what that'll do is mean that you're getting excessive voltage. I think if I'm recalling correctly, the relationship between those. But in any case, my hypothesis is that these resistors have drifted. That changes the amount of current flow through here, which in turn changes the current flow that we're programming for when we change these resistors, right? You can see if there was only 0.5 milliamps flowing through this, well, the resistance here that would produce equilibrium at 0.5 milliamps would be, different. So that's why it still responds to changes in the voltage. It just doesn't respond in the correct magnitude. The magnitude is wrong because we're no longer having the correct current flow through here. And so my hypothesis is that we need to look for the resistors that are in this unit analogous to R14, R16, and R17, and I think that these will be low in value. And I think another thing we could do is try testing the current through here and seeing if it is the 1 milliamp we expect or if it is some other value that would indicate that there's an issue with these resistors. So now that we have a hypothesis about what might be wrong with this power supply, I realize there's actually a very easy way to test it. So remember earlier I showed you that there are these two terminals on the back to add your own external resistance to set the voltage control. And of course what that's doing is just putting whatever resistance goes between these two terminals in series with the resistors that are internal to the unit in the voltage control circuit. So these two terminals should also have 1 milliamp passing through them since they are in series with the rest of the resistors that we use to set the voltage. So an easy way to check if we have the correct amount of current flowing is just to hook a DMM up to these two terminals and put it in current mode. And of course we're going to see now how much current is flowing through the voltage programming resistors. And remember, as we just discussed, based on the schematic, that should be 1 milliamp. If this is 1 milliamp, that means we have the correct amount of current flowing. Anything other than that will introduce an error in our voltage setting. So without further ado, let's just turn this on and see what we get. All right, there we go. So we have 2.1 and climbing milliamps flowing through our voltage programming resistor circuit here. And that's only supposed to be 1. And remember, as I discussed earlier, excessive current flow through here will cause excessive output voltage. So what we observed earlier when we first started the video is that our output voltage was about 2.2, 2.3 times higher than the meter dials on the front suggested it should be. And well, this is the explanation. Our current flowing through that circuit is also about 2.25 times what it's supposed to be. So I think we have managed to figure out what the issue is with this unit. Now it's just a question of tracking down those three resistors on the in the actual unit itself, and and finding out which one or ones are responsible. And I'll of course have to order new ones. I would like to keep these, very nice, low wattage as they're originally spec'd, temperature, good, temperature coefficients, good ppm drift resistors in this thing. So we're going to want to order replacements, even though I could make something with a trim pot and with resistors that I already have, but we want to do something nice for this. So let's go track down those faulty resistors. I think it was R14, R15, and R16, and let's get them replaced. All right, so this is the underside of the Power Designs 4010. So that board we had been looking at the top of earlier, this is the bottom of it. So the oven is right here in the middle with all these pins on it, and then of course we've got these really pretty gold trimmers. We have these are also trimmers. Actually, they're really big multi-turn trimmers. This would be the modern equivalent, and you can see it's much, much, much smaller. So yeah, huge multi-turn trimmers, got some caps. We have our transistors, of course, and it's nice to see that the leads are still nice and golden. Nothing looks corroded down here. This would be the one differential pair transistor that's not potted, so that's not ovenized rather. So that would be Q9. And anyways, but the reason we're down here is to try to figure out what went wrong with this, with our resistors specifically. So because that's what our theory is, we're going to see if it's correct and see if our resistance checks out. So if I show the schematic again just for 1 second, you can see that the resistance of the three resistors that we're suspecting, R14, R16, and R17, can be measured by measuring the resistance between pins 3 and pin 2 on our oven. So of course this unit is not a 2005A, which is the schematic we have. So we have to just hope that the pinout on the oven is the same, although I would suspect that it is the same. Not really much reason to change it. The oven has the same amount of pins. It has 11 pins, just like on the 2005A. So I'm gonna make an educated guess that the pinout is the same. But let's see if the result we get makes any sense. So let me reposition the multimeter here. Actually, I'll just have to reposition the camera probably. Maybe I can. All right, that's good enough. Let's place our leads on pins 2 and 3 and see what we get. Okay, so we're actually getting 5.9 k ohms, actually 6 k ohms. So interestingly, that's actually not that far from the value that the resistors are supposed to be. In fact, it's pretty close. We were expecting the resistors to be off by a factor of more than 2 in order to produce our incorrect voltage, which is off by a factor of more than 2 as well. But actually the resistance is only off by about 200 ohms, which isn't that big of a deal. However, remember this is not a 2005A, this is a 4010. And so if the Zener voltage difference between pins 3 and 2, because remember we said the Zener is what generates that voltage difference, if that Zener is a different value, then our resistors should also be a different value to produce the correct current flow through the current setting circuitry. So let's check if our Zener is actually the same voltage as the one in the schematic. And if it's not, then we need to adjust what we expect the resistors to be as well. So we can check the voltage of the Zener by putting a voltmeter across pins 7 and 2. So I'll just show the schematic really quickly. Again, you can see 7 and 2 as we mentioned earlier. That gives you the difference in voltage across CR9. So let's try that now. Here's 2. Gotta get these safely mounted so when I turn this on, we're not causing any problems. Okay. There's 2, and there's 7. I think that's good enough. So in order to get the incorrect, if the resistors are actually the problem, let's phrase it this way, if the resistors are actually the problem in the way I expected, then we should be looking for a Zener voltage that is like 13 volts, I think, because that would mean our resistors would, in fact, be more than 2 times too low. So let's just see what we get. I'm going to turn on our line right here, and then let's give it like 10 seconds just for the oven to get a little hot. I doubt it matters, but all right. And now let's turn on the unit itself and see what our Zener voltage is. All right. Yep. Zener voltage is actually 13.4, probably higher, 13.5. It's probably going to keep climbing a little bit. I'll just let it stabilize. But all right. So even though our resistor value is actually close to what's on the 2005A schematic, our Zener voltage is more than twice the value that's on the 2005A schematic. So in fact, our resistors are low as expected. So what's left to do now is to determine which resistor is low, and then we know which one to replace, because remember there are 3 resistors that set the resistance between those 2 points, and it could be, It could be any one of them that's gone low to cause this problem. Well, it probably couldn't be R17, which is the variable resistor, because even if that went all the way low, we wouldn't get the issue that we're seeing. But anyways, yeah, so our Xander is about 13.6 volts. So that is 7 volts lower than the value on the schematic, which makes sense. So the issue is indeed that our resistors have gone low. And what we're going to have to do is trace the circuit a little bit so we know which resistor we need to we know which point we need to disconnect. I hope it's not the resistor inside the oven that's gone low. I hope it's the one that's mounted to the board, because I don't really want to have to remove the insulation from the oven and unpack the oven, which would be a pain. It does have some sort of a glass fiber or asbestos insulation inside of it, I think. I hope it's not asbestos. I mean, it's such a small quantity, it wouldn't really matter. But there's some sort of an insulation in there, and I know that once I open the oven, it's going to get everywhere, and I'm going to have to repack it. So really holding out for the resistor that's mounted to the board being the problem, and we're going to have to trace the circuit and identify that resistor, which shouldn't be too difficult since this is all kind of point-to-point wiring here. All right, so with just a quick bit of tracing through the circuit here, I did manage to find our R16 and R17. So this right here, of course, being R16, you can see the 49.9 k ohms printed on the side, and of course it is a 1% precision resistor, as you'd expect for this precision voltage setting circuitry. And of course we do have our 17 right next to it, which is a trimmer right here. So that is used to adjust things really finely. They're not just purely relying on the precision of these resistors. You do have an adjustment there. So this is our 17, our voltage adjust trimmer, and this is our 16. So as I said earlier, if you look at the way this thing is built, R17 alone failing wouldn't cause this sort of an issue, since R17 and R16 are in series, and even if R17 went completely shorted, you would still have the 49.9k resistance of R16 in series there. So that still wouldn't lower the resistance enough to give us the problem that we're seeing. So really, it has to be an issue with either R14 and or R16. R17 could have a problem as well, but that alone wouldn't be sufficient to cause this issue. So really, I'm going to be looking at this guy right here. And what we're going to have to do, because obviously if you look at the schematic, it's not possible to test the resistance of just this in circuit, because it's in parallel with all the other stuff, with the other two resistors, R14 and R16. We're going to have to disconnect one leg of this resistor. I think what I'm going to do is just heat up this this little eyelet right here, and then try to lift this lead out of there so that we can get a good resistance reading on this. Of course, that will disconnect this from the circuit, and that'll also allow us to read the value of R14, which is inside the can, by simply taking the measurement between pins 2 and 3. So let's get right to that. All right, so now I have the leads hooked to pins 2 and 3 of the oven, and you can see the resistance that we're measuring here should just be R14 alone now, since we've disconnected R16, and we get about 6.84 k ohms. So that should be, the resistor should be more than double what the 2005A schematic specifies, and that's 7.2k. So this is already below that. It should be more than double that. So this is clearly way too low. So that's our problem. And we're going to head over, of course, to the parallel resistor calculator, because I'm lazy and don't want to do math the normal way, and we'll figure out what we need to order as a replacement for this resistor to get things working again properly and to get our 1 k ohm per volt relationship back into this circuit. And yeah, I'm going to do this without opening up the can because I don't want to open up the can at the moment. So we're just going to do this theoretically and hope it turns out well. All right, so I won't be showing you the parallel resistor video I shot because I was wrong. It's not the resistor. It's not R14 that's the problem. It is the voltage between pins 7 and 2 that is the problem. So let's quickly go over what I did. Before ordering the new resistor, I decided I would open up the oven just to make sure and see if I could find R14 and see the value that it was supposed to be. So I opened up the oven. You can see it right here. You know, it had this thing on the outside of it, but I pulled it off. And this is what the oven looks like. The heating element, you can see it's this kind of ribbed wires in there. This is the oven. It has this inner metal tube, and then inside of this tube is the actual PCB. And we can also see this is the PCB. There's some glass, fiberglass wool in there. So the PCB does not come out of this tube. I've tried really hard. I've yanked on it with pliers. I've done a lot of things. It's stuck in there. I think it's glued at the bottom or something. However, thankfully, R14, the resistor R14, was actually right at the top of the PCB. And I could tell that it was R14 because there's only one precision resistor in this thing, and the resistor I pulled out is a precision resistor. So this has got to be R14 from the oven. And if you remember our hypothesis, I was saying, oh, if the voltage between pins 7 and 2 is 13 something volts, then this R14 should be like 18k ohms to give us our proper 1 volt per ohm and whatever relationship. However, so we would expect this to be 18k if I was right that this resistor is the problem. It's not 18k. It's the value we expected. It's 7.2k, which we thought 6.8, whatever. However, printed on the resistor is 7.2k. So this resistor has not drifted. It's not supposed to be 18k, and it drifted to 7.2k. It's always been 7.2k, which means the only other conclusion is that our voltage between pin 7 and 2 is not supposed to be 13 point whatever volts. It's supposed to be 6.3 volts, just like in the 2005A oven, because our R14 is supposed to be the same value as the 2005A oven. So in reality, I think it's the Zener voltage reference diode in the oven that's our problem and not R14. Unfortunately, because I can't get this PCB out of the oven, I don't know how I would go about fixing that diode, or maybe it's not even the diode itself, maybe it's some of the other circuitry surrounding it. I don't even know how I would go about fixing that because this thing is stuck in there. So rather than like cutting this open and trying to fix it, which would probably break the heating element and whatnot, I've decided the best way to fix that issue with the voltage between pin 7 and 2 is to just make a new oven. So I already put one transistor on it because I was getting bored. But anyways, that's the differential dual NPN BJT that we saw earlier for the differential kind of amplifier part of it. And then I also have this, which is a MS2270. That's the other transistor on this board. I ordered these both off eBay. I think this is an exact replacement. I think this is a close equivalent. And then I have what I believe are replacement Zener diodes. I have replacement normal diodes. I actually got these used. They're the same diode. And then I have all our resistors here. So what we're going to be doing in order to get this oven fixed is actually to just replace it completely with a new board. It's a little bit disappointing because I thought that since we knew what the issue was, since we really isolated the part of the circuit that the issue was in, I thought we wouldn't have to do like a big replacement like this. I thought we could, do component level troubleshooting, and I think we could have if I could get into that oven. I think now we know that it's got to be that Zener or something very near that Zener that's causing the problem because our voltage is wrong, but just nothing I can really do about it. So the solution is going to be try to build a new oven board. Of course, this one isn't actually ovenized, so it's not going to have the temperature stability that this one does. It doesn't really matter for my application. Honestly, I don't really care about the temperature stability. I just want really good regulation and low noise. So this doesn't really, not a huge difference for me. But anyways, we're going to populate this new oven board with parts and hope that it works. I do have 9 more of these because I had to order a decent amount. They were so cheap because they're so tiny that it was stupid to order like anything less than 10 of them. So I ordered 10 of these. If anyone needs to rebuild 2005A or presumably 4010 ovens, I have these. I did make one mistake, so you'll have to bodge one resistor onto the bottom. I apologize for that. I did make a mistake. With the schematic, I left one resistor out. So anyways, but yep, so right now we're just going to, I'm going to solder this board together, and we're going to hope that it works. All right, so here is the oven replacement board. I've got it all soldered up. I cut the leads except for, as you can see, the leads to the transistors. I did leave those long in case there's any issues with this board or I need to remake it or anything. I could reuse those transistors because they are a bit valuable. But otherwise, I clipped all the leads, everything soldered on here. I forgot that R8, which is the 7.2K precision resistor. I couldn't find a good 7.2K through-hole precision resistor to use on Mauser, so I bought a 5K in a, I think, actually, I don't remember if I bought a 5.2K in a 2K or a 5K in a 2.2K, but in any case, yep, a 5.2K right here, you can see 5.2K, and then a 2K. So that's those are in series to give us our 7.2K ohms for that R8, but otherwise everything is just standard. And then we of course have our bodged resistor on the bottom here. As I said, I made a mistake. I forgot to include this 200K resistor, and I forgot to include test point 6 as well, which is one of the, I named these all test point, but it's one of the pins on the oven. It would have been pin 6. So I forgot to make a connector for pin 6 and include this resistor, so I've just bodged it onto the bottom here and put a little piece of Teflon sleeve on there so that it doesn't get shorted against anything. But yep, other than that, this is the little board. It fits nicely into the hole, as you'll see in a second. I need to solder the wires onto here that connect to the actual eyelets on in the unit, but once we do that, we'll be ready to connect this and fire it up. All right, so here's my PCB secured to the phenolic board and connected using the wires to the corresponding test points. As you can see, it's not my neatest work ever. I didn't have really a great size of solid core wire. I wanted to use solid core because it's much easier to get them into these eyelets. And I didn't really have a good size solid core. I have some smaller ones, but they have a really thick insulation that's not very flexible, so I opted to use this kind of thick 18 gauge solid core wire. Unfortunately, Its insulation didn't fare very well against the heat that was necessary to get these into the eyelets, because they're so thick. They have to kind of really be pushed in there. So yeah, so some of the insulation got a little bit messy. Luckily, these are really thick wires, so they're not going to flex much, so I'm not too concerned about them shorting out or anything like that. And yep, so I've got everything connected up, and I guess we're just going to turn this on and see how it goes. But I'll also show you the back. This wire right here was connected to test point 6, or point to pin 6 on the oven. That's the one that I had to bodge, so that does go up and around the board and connects on the other side. I'll show that really quickly. Alright, so here's what it looks like on the top side. You can see I did clip the leads a little bit just because they were ridiculously long, and I don't want them shorting out or anything. And you can also see the bodged resistor, and it just goes to the other side with some heat shrink that connects to one of the wires. Alright, so now that the PCB is wired in there, we should be ready to turn this thing on. I've got the DMM hooked up here, reading the voltage on the output terminals. I clipped it with mini grabbers to the back side of the terminal, but it is connected to these two terminals. And then I also have, in the back here, you can't really see it, but this is set up as an ammeter, a multimeter reading amps in the back there. You know, obviously we shouldn't be drawing very much current here because we don't have any load on the power supply except for, you know, whatever the load of the multimeter is. So yep, so that's what we've got here. So this will be reading, of course, the output voltage, and I've set it to 5. I don't know if you can see it here, but 0500. So this should be around 5 volts. So without any further ado, I also have it hooked up to a dim bulb tester. You can't see it, but there is a dim bulb tester up and to the right. So let's turn this on and see what happens. All right, not bad. It looks like we do have about 5 volts. It's climbing a little bit. Actually, it's dropping. After it first turns on, I'd expect a little bit of instability. We actually had some instability with the oven too. Of course, you know, we know that the Zener in there was misbehaving. So, and of course, we no longer have the temperature stability of the oven anymore. So it's going to be drifting quite a bit more. But other than that, it looks like it's working. We have about 5 volts, 5.03. So obviously we are off by a little bit, and we do have our calibration points right up here. I don't know if you can see them, but we have voltage calibration and then our 0 as well. So what I'm going to do now is actually just leave this running, leave this on, and I'm going to leave it on for about a half an hour, and then I'm going to come back and I'm going to calibrate this. So yep, and I'm going to show a time lapse, I think, and so that way you can see how our voltage is drifting around a bit, given that we no longer have our temperature stabilization. This might be somewhat of an issue, you know, if you needed a lot of temperature stability. I'm planning on using this as a power supply for tube amplifier stuff, for providing DC for tube bias and stuff like that. So I'm not too concerned with, you know, having insane temperature stability at the tens of millivolts or whatever. Usually in tube gear, all the voltages are kind of ballparked anyways with tube gear. Nothing's usually really regulated that tightly. So this thing is more than good enough for my purposes. Of course, if you were using it for its original purpose, you might be wanting some better voltage stability, but of course you don't get that with this PCB. You just get, you know, you get the stability of the unovenized Zeners and the transistors that aren't necessarily thermally mated or anything like that. So yep, let's leave this on for a bit and see where the voltage settles. Alright, so now the power supply has been on for about a half an hour. And as you can see in the time lapse, it's stabilized at about 4.998 volts, and it's going down to 4.9978 or 79 and back and forth a little bit, but it's pretty stable at this point. The variation is in the single millivolts range. Actually, it's less than that. It's in the tenths of a millivolt range, because it's just going from 998 down to 9979, 9978, and whatever. So that it is very, very stable at this point. Now that it's reached some sort of a thermal equilibrium, it is very stable. But obviously it drifts for quite a while after being initially turned on, which isn't ideal, but it is nice that it does reach a stable voltage eventually. So if I need to use this for running any experiments or whatnot, I can be pretty confident that if as long as I leave it on for 20 to 30 minutes, it is holding a pretty consistent voltage here. All right, so now it's time to do the calibration. We have our two calibration trimmers for the voltage offset and our voltage calibration right here, and they're labeled. And there's a cutout in the side so you can access them there. I think intuitively, so one of them sets the 0 point, so it sets the voltage at 0 when the voltage on the front dials is actually set to 0. And the other one sets the current through our voltage programming resistor network that we discussed at length earlier. And I think it's obvious intuitively that the 0 needs to be set first, because you don't know how much error there is in the voltage setting network if you don't know that your 0 point is actually set correctly. If your 0 point's off by a couple hundred millivolts, then you're going to be setting, using this trimmer, the wrong relationship between 0 and whatever voltage you're at. Hopefully that makes sense intuitively. But anyway, so we're going to calibrate the 0 first. So what I'm going to do is just switch our voltage here to 0 on the front, using our dial at the front. All right. And keep in mind, I did leave this on this entire time, so it has been on for a while, so hopefully, we've kind of aged that in. And so when we set this, we'll be setting the right relationships for once it kind of reaches thermal equilibrium. Okay, so it looks like left is decreasing this. I don't know if I'll have enough adjust range to get this to 0. It doesn't seem like this changes it very quickly, so that could be a problem. Ooh, yeah, we are out of adjust range, it seems. So it does seem that I don't think that we have any more adjust range on the 0 set. So unfortunately, we might just have my oven replacement might not really be designed correctly to get this zeroed out 100%, which isn't too surprising. I mean, my Zener might be a little bit different than the one that they used. And some of our transistors might be, a little bit different than the ones that were supposed to be used. So it's definitely possible that we're outside of the adjustment range that this thing was built for, and it's not possible to zero this out. So what I'm going to do then is set the correct voltage relationship at 30 volts or 40 volts, which is the maximum. And so, I think that's the best we can do. We're just going to have to accept that we have a little bit of offset. And so on the low ranges, then the voltage will be a little bit low. Another way I could do it is to set it so that at 30 or something, it's actually 30.1, and then we could just always assume that or 30.01, then we could just always assume that there's a 0.01 voltage offset. But I don't think I'm going to do that. I think I'm just going to set it to the correct voltage, and all the other voltages will be a little bit high, I guess it would be. The low voltage will be a little bit higher than what's read on the front dial. Although actually, let me make sure I'm zeroed on my, yeah, I am. Okay, so now it's zeroed on the, it's zeroed even on the 0 to 10 millivolts range. So we're still off by a little bit. So I think that's the best we're gonna get. And let's put it up to a higher voltage, and we can set the voltage scaling. All right, so now we should be at 30, and I'm going to adjust this one for 30. Okay, that's the most adjust range we get out of this one. Yep, that's all we got out of this one. So 29.9 is all we get when it's set to 30. So yeah, clearly we're off by a little bit, it seems, unless my multimeter's off, but I don't think it is. So yeah, but I don't think we're going to get it perfectly zeroed, and I don't think we're going to get the voltage relationship quite right. So unfortunately, we don't have the same amount of precision that this thing came with. We don't have the ability to be fully confident that what's on the dials at the front is, the exactly correct voltage. Although, given the fact that the offset is high, but the voltage ratio is a little bit low, it actually means that in the middle ranges, this thing does read the correct voltage. So for instance, right now I'm set to 20 on the front panel, and it's pretty close to 20. Maybe if I go down to something like 15, I think we're gonna have pretty damn close. Yeah, so that's 15, and we're still pretty damn close. So it is close, but obviously it's gonna be off by a little bit, and we just ran out of range on the calibration because I think we're a bit out of spec for what the calibration, resistors were designed to compensate for. I think that's fully to be expected, considering these are just random components I put in there, and the original oven was like a precision designed part specifically for this unit. It would have had much better tolerances. They could have been hand selecting components in there to make sure everything was within tolerance. You never know. So we've got it close enough, and certainly good enough for my purposes. And if I were to use this for anything really precise, I would check my voltages with a DMM rather than trusting the dials on the front. And since we've seen it is pretty stable, I mean, look, right now it's holding 4.986 like perfectly. It is stable once the voltage is set properly and once it's warmed up, but I will just need to double check with the multimeter if I need really, really good precision. All right, so I've got the Power Designs 4010 reassembled here and running and turned on. As you can see, it's outputting 10 volts or close enough to it. I took care of a few minor things, such as cleaning the flux off the back of the PCB and clipping the leads and so forth, and I reassembled it. So it's running here now, and you can see obviously when we change the dials on the front, we get the corresponding change in voltage. So yeah, working pretty well. Sometimes I think I could deoxit the switches. I think the actual switch contact resistance is sometimes messing with our voltage a little bit, because sometimes when you flip the switches back and forth, you'll get a slightly different voltage. Anyways, there are a few minor things that I could do like that, but overall, I'm really happy with how this repair turned out in the end. Obviously the solution that I ended up arriving on with replacing the oven with, a PCB doesn't necessarily retain the voltage stability over time and against temperature variation that the original had. And we also don't have the, spot on ability to set the voltage using the dials at the front because, as I discussed during the calibration, we can't zero this perfectly, and we can't adjust the voltage, network compensation fully, but we're close enough here. I mean, we're like tens of millivolts, if not millivolts off on most of these settings. So I think that's pretty good, especially for my purposes. I mean, what I really wanted out of this was a nice low noise linear power supply. And obviously, it might not perform up to the original spec, but it does still have low noise. If we switch the DMM here to AC millivolts, we can see that we have less than a millivolt of AC on this output. And of course, the frequency response of this is limited, but I don't think we have any like high frequency noise going on here. It's a linear supply. We really just have, 60 hertz and, ripple and whatnot, 120 hertz rather, probably, ripple and whatever. But you can see that our AC component here, as measured by the multimeter, is below a millivolt. So still a very nice, low noise power supply, and still very good regulation and all that. So that's what I really wanted from this anyways. The voltage accuracy is more than enough for my purposes. So yeah, I am happy with how this turned out in the end. And that's going to be it for this video, I think, because there's not much else to do. I'm not going to recap this thing. I'm not going to replace all the lights and stuff. I have so many other projects to get to. I could do that stuff later on, but I think the capacitors in here are all good. There's no signs of capacitor failure anywhere in the functioning of this. And those metal encased Sprague capacitors tend to be very high quality, long-lived capacitors. So not too worried about that. Of course, some of the lamps are a little dim and stuff like that, but for my purposes, I don't really think that the time involved in repairing that stuff is really worth it, at least right now. If I really wanted this to be, and this is never going to be an original museum quality piece anyways, because I've gone and replaced the oven with my own board in there, so there's that. But this thing looks really great. It's built phenomenally well, and I got it for super cheap, so I'm very happy that I was able to get it working at least in the end, and have a nice working low noise linear power supply. If anyone wants these PCBs, I would be more than happy to send them to anybody for the price of shipping. I'm also planning to upload the KiCad schematic and PCB files all to the internet so that people can use them if they need to. They could correct my mistakes and add a test point 6 and that extra resistor into this thing if they wanted to, although of course it's such a small PCB, getting it fabricated is a pain. You might rather just get one of mine. I'll send it for cost of shipping. I have no use for them now. I don't think I'm gonna run a repair business, fixing these up. So yeah, if anybody wants those, I'd be more than happy to send them. And yeah, I have a ton more projects in the pipeline, a lot more, at least 6 to 7 things that I need to work on immediately. So there's definitely going to be more coming soon, in case that's something you're interested in. So thanks for watching, and I hope the video was interesting.